In the vast, unending expanse of the cosmos, a breathtaking drama unfolds. Stars, the celestial giants of our universe, blaze with unimaginable fury. For eons, they illuminate the darkness, anchoring solar systems and painting galaxies with streaks of light. But even these titans are not immune to the passage of time. Stars like us have a life cycle. They are born, they shine, and ultimately, they meet their end. And what an end it is! This final act, a cosmic spectacle of unparalleled proportions, is known as a supernova. Imagine a star, millions of times larger than our own sun, finally succumbing to the relentless pull of gravity. Its core collapses inward, triggering a chain reaction that culminates in a blinding explosion. For a brief, glorious moment, a supernova can outshine an entire galaxy, its light a beacon across the universe. This isn't just destruction on a grand scale, it is a transformative event. Supernovae are the universe's alchemists, their fiery furnaces forging the building blocks of life itself. The iron in our blood, the calcium in our bones, the gold in our most prized possessions, all were born in the heart of a supernova. To understand the awesome power of a supernova, we must first journey into the heart of a star. Stars are fueled by nuclear fusion, a process where hydrogen atoms fuse to form helium, releasing tremendous amounts of energy. This outward pressure from fusion battles against the relentless inward pull of gravity. For much of a star's life, these forces exist in an intricate balance. But this equilibrium cannot last forever. As a star ages, it gradually exhausts its supply of hydrogen fuel. The outward pressure of fusion weakens, and gravity begins to gain the upper hand. The star's core contracts, heating up to unimaginable temperatures. This triggers new fusion reactions. Heavier elements like carbon and oxygen begin to form. The star enters a period of intense change, expanding and contracting as it struggles to maintain equilibrium. Its outer layers pulsate, casting off vast clouds of gas and dust into space. These stellar winds carry the elements forged in the star's core, seeding the interstellar medium with the raw materials for future generations of stars and planets. The fate of a star and the type of supernova it will ultimately produce depends on its mass. Stars like our Sun, relatively small and unremarkable, will eventually shed their outer layers, leaving behind a dense, cooling ember known as a white dwarf. While beautiful in its own right, a white dwarf's story is relatively quiet compared to its more massive brethren. Massive stars, those at least 8 times the mass of our Sun, are destined for a far more spectacular demise. As they exhaust their nuclear fuel, these stellar giants face a catastrophic collapse. The core implodes, collapsing in on itself with unimaginable force. This generates shock waves that rip through the star's outer layers, blasting them apart in a brilliant explosion. This is a Type II supernova, a cosmic titan's final glorious curtain call. Deep within the heart of a massive star, a battle rages. For millions, even billions of years, a delicate balance has been maintained. The outward push of nuclear fusion, the very engine of the star's existence, has held against the relentless inward pull of gravity. But this cosmic dance cannot last forever. As the star exhausts its nuclear fuel, the fires of fusion begin to sputter and fade. The outward pressure lessens, weakening the star's defenses against its own immense weight. Gravity, patient and persistent, senses its opportunity. Like a cosmic python, it begins to tighten its grip. The core, once a furnace of unimaginable power, starts to contract under the relentless pressure. Atoms are crushed together with unimaginable force, pushing the core's temperature to billions of degrees. The star is fighting for its life, desperately trying to ignite new fusion reactions to counter the gravitational collapse. But gravity is a relentless foe. As the core contracts further, its density skyrockets, approaching the point where even the very fabric of space-time begins to warp and distort. The star's fate is sealed. It is hurtling towards a cataclysmic demise. In these final moments, the core of the star transforms into a crucible of incredible density and temperature. Electrons are forced into the very atoms they once orbited, merging with protons to form neutrons. The core is no longer a swirling inferno of plasma, but a tightly packed sphere of neutrons, a cosmic nucleus of unimaginable density. This neutron core, while incredibly small, perhaps only a few miles across, resists further compression. It becomes a cosmic fortress, a last stand against the crushing weight of the star bearing down upon it. For a brief, fleeting moment, an equilibrium is reached. But this reprieve is short-lived. The outer layers of the star, still drawn inward by the relentless pull of gravity, slam into this unyielding neutron core with unimaginable force. The impact sends shockwaves reverberating through the star's interior, pushing temperatures even higher. The core, now a superheated neutron star, becomes a crucible for the creation of the heaviest elements in the universe. Gold, platinum, uranium, elements far too heavy to be forged in the normal life cycle of a star, are born in these final, frantic moments. The shockwaves from the core's collapse propagate outward, ripping through the star's interior like a sonic boom. They gain momentum as they travel, carrying with them the energy of a billion suns. These shockwaves are the harbingers of the star's impending doom, a cosmic tsunami about to unleash its fury. As the shockwaves reach the surface, the star's outer layers erupt outward in a cataclysmic explosion. This is a Type II supernova, the explosive death throes of a star many times more massive than our Sun. It is a spectacle of unimaginable power, a cosmic fireworks display visible across billions of light years. The star's remains, a chaotic nebula of gas and dust enriched with heavy elements, are scattered across the cosmos. These remnants, forged in the heart of a dying star, will eventually coalesce to form new stars, planets, and perhaps even life itself. The death of a star, though violent and destructive, is an essential part of the cosmic cycle of creation and destruction. It is a reminder that even in the vastness of space, nothing is truly permanent, and that even in death, there is a breathtaking beauty and a profound sense of awe. So far, we've journeyed into the heart of a massive star, witnessing its final, fiery demise as a Type II supernova. But the universe, in its infinite creativity, offers another path to this explosive end Type I supernovae. These stellar explosions, while equally dramatic, arise from a different set of cosmic circumstances. Type I supernovae occur in binary star systems, where two stars are locked in a gravitational dance around a common center of mass. Imagine two celestial partners, eternally entwined in a cosmic waltz. But this dance, like all things in the universe, is subject to change, sometimes with cataclysmic consequences. Within these binary pairs, one star may age faster than its companion. If this star is similar in size to our Sun, it will eventually evolve into a white dwarf, a dense, Earth-sized remnant of its former self. White dwarfs are incredibly faint, but don't let their dimness fool you. They still harbor immense gravitational pull. Now, imagine this white dwarf, a stellar ember still radiating heat from its long-gone youth, orbiting in close proximity to its companion star. Here's where the story takes a dramatic turn. Like a cosmic vampire, the white dwarf can begin to siphon off material from its unsuspecting neighbor. This stolen material, mostly hydrogen and helium, forms a swirling disk of gas around the white dwarf, known as an accretion disk. As more and more material spirals inward, the white dwarf's gravity compresses and heats this stolen bounty to incredible temperatures. Remember that a white dwarf is essentially the exposed core of a dead star, rich in carbon and oxygen. As the temperature of the accreted material skyrockets, it reaches a critical point where these elements can undergo a runaway fusion reaction. Imagine a spark igniting a powder keg. That's what happens when the stolen material on the surface of the white dwarf reaches the critical temperature for carbon fusion. The fusion reaction spreads like wildfire throughout the entire white dwarf, engulfing it in a thermonuclear inferno. Unlike a Type II supernova, where the core collapses and rebounds, a Type I supernova is a complete and utter annihilation. The white dwarf is completely consumed in the explosion, leaving behind no remnant core, no neutron star, only a rapidly expanding cloud of superheated gas and dust. This explosion, while different in origin from a Type II supernova, is no less spectacular. In fact, Type 1 supernovae are often even brighter than their Type 2 counterparts, shining with the brilliance of billions of suns. Both Type 1 and Type 2 supernovae, though born from different stellar paths, share a common legacy. They are the universe's grand recycling plants, seeding the cosmos with the elements essential for life. The intense heat and pressure within these stellar explosions forge elements far heavier than iron, elements that cannot be created in the normal life cycle of stars. These heavy elements, scattered far and wide by the supernova's shockwaves, enrich the interstellar medium, the vast clouds of gas and dust that permeate galaxies. From these enriched clouds, new generations of stars and planets will eventually form, each carrying within them the echoes of these ancient, cataclysmic events. So, the next time you marvel at the twinkling stars, remember that some of those distant suns are destined for a far more dramatic fate. They will erupt as supernovae, cosmic fireworks that illuminate the universe and seed it with the very building blocks of life itself. Throughout human history, the night sky has been a source of endless fascination. Ancient civilizations looked upon the stars with awe and wonder, weaving tales of gods, heroes, and mythical beasts among the constellations. But the heavens are not static. They are a canvas upon which the universe paints its most dramatic stories, and few events are as captivating as the sudden appearance of a new star, a supernova, blazing forth with the brilliance of 1,000 suns. Imagine yourself transported back in time to a world illuminated only by firelight and starlight. One night, as you gaze upon the familiar tapestry of stars, a new light emerges, a celestial interloper disrupting the celestial order. This brilliant beacon, shining even brighter than the planets that grace our skies, is a supernova, announcing the death throes of a distant star. These celestial spectacles, though fleeting, left an indelible mark on the annals of human history. Long before the invention of the telescope, ancient astronomers meticulously recorded the appearance of these guest stars, noting their positions and tracking their brightness over time. One of the most famous supernova events in recorded history occurred in the year 1054 AD. Chinese astronomers, renowned for their meticulous observations of the heavens, noted the appearance of a new star in the constellation Taurus the Bull. This celestial newcomer was so bright that it was visible even during the day for nearly a month, casting shadows at noon and captivating the imagination of all who beheld it. Half a world away, Japanese and Arabic astronomers also documented this extraordinary event, adding their own observations to the growing body of knowledge about these celestial wonders. These ancient records, meticulously preserved over centuries, provide modern astronomers with invaluable insights into the life cycle of stars and the nature of these cosmic explosions. The remnants of this ancient supernova, known today as the Crab Nebula, still adorn the constellation Taurus. This expanding cloud of gas and dust, glowing faintly with the light of its long-dead progenitor star, serves as a poignant reminder of the transient nature of stars and the enduring legacy of supernovae. In modern times, the study of supernovae has moved far beyond simple observation. Armed with sophisticated telescopes and instruments, astronomers can now dissect the light from these distant explosions, revealing their secrets in exquisite detail. Supernovae have become cosmic lighthouses, their brilliant beacons guiding us through the vastness of space. One of the key insights gleaned from studying supernovae is their remarkable uniformity. Type Ia supernovae, in particular, exhibit a consistent peak brightness, making them invaluable tools for measuring cosmic distances. By comparing the observed brightness of a Type Ia supernova to its known intrinsic luminosity, astronomers can calculate its distance with remarkable accuracy. These standard candles, as they are known, have allowed astronomers to chart the expansion history of the universe, leading to the groundbreaking discovery that the universe is not only expanding, but doing so at an accelerating rate. In Section 4, Unraveling the Universe, we delve into one of the most profound mysteries in modern cosmology, the accelerating expansion of the universe, driven by the enigmatic force known as dark energy. Supernovae, through their role as cosmic distance markers, have provided some of the most compelling evidence for this perplexing phenomenon. By observing distant Type Ia supernovae, astronomers have discovered that they are fainter than expected, suggesting that they are farther away than predicted by a universe expanding at a constant rate. This unexpected faintness implies that the expansion of the universe has been speeding up over time, as if some unseen force is pushing galaxies apart with ever-increasing vigor. The study of supernovae has opened new windows into the cosmos, revealing the universe to be a far stranger and more wondrous place than we ever imagined. These celestial explosions, once shrouded in mystery and superstition, have become essential tools for unraveling the deepest secrets of the universe, from the nature of dark energy to the fate of the cosmos itself. In Section 1, Deciphering the Light, imagine a supernova exploding billions of light years away. The light from that explosion, carrying with it the story of the star's demise, begins its long journey through the cosmos. As this light travels through space, it encounters clouds of gas and dust, its path subtly altered by the gravitational pull of galaxies and the expansion of the universe itself. When this light finally reaches our telescopes, it arrives bearing the imprint of its long journey. Astronomers, like cosmic detectives, can analyze this light, deconstructing it to reveal the secrets encoded within. By studying the spectrum of a supernova's light, they can determine its chemical composition, its temperature, and its velocity. This analysis goes beyond simply understanding the supernova itself. It provides a glimpse into the nature of the space between the stars, the interstellar medium, revealing the presence of elements and molecules that would otherwise remain hidden from view. In Section 2, The Expanding Universe, perhaps the most profound use of supernovae as cosmic tools comes from their role in measuring the expansion of the universe. As we've learned, Type Ia supernovae, those stellar explosions born from the demise of white dwarf stars, serve as standard candles. Their consistent peak brightness allows astronomers to calculate their distance with remarkable precision. By observing Type Ia supernovae at different distances from Earth, astronomers can track how fast the universe has been expanding at various points in its history. What they have discovered, to their astonishment, is that the expansion of the universe is not constant, but is, in fact, accelerating. This discovery, one of the most surprising and significant in modern cosmology, has fundamentally altered our understanding of the universe. It implies the existence of a mysterious force, dubbed dark energy, that is counteracting gravity and driving this accelerated expansion. Section 3, Beyond the Visible Dark Energy. Dark energy, so called because it does not interact with light and therefore remains invisible to our telescopes, constitutes the vast majority of the energy density of the universe. Its existence, inferred from the accelerating expansion of the universe, represents one of the greatest unsolved mysteries in modern science. Supernovae, through their role as cosmic distance markers, have provided some of the most compelling evidence for the existence of dark energy. By studying how the brightness of distant supernovae dims with distance, astronomers can map the expansion history of the universe and infer the influence of this enigmatic force. The nature of dark energy remains elusive, but its discovery has revolutionized our understanding of the cosmos. It suggests that the universe is not only stranger than we imagine, but stranger than we imagine. Section 4, Echoes of Creation. Supernovae, those spectacular explosions that mark the end of a star's life, are not merely destructive events. They are also engines of creation, forging the heavy elements essential for life and seeding the interstellar medium with the raw materials for future generations of stars and planets. The light from these distant explosions, carrying with it the story of stellar death and cosmic expansion, serves as a cosmic time machine, allowing us to peer back into the history of the universe and unravel its deepest mysteries. Each time we observe a supernova, we are witnessing a fleeting glimpse of a cosmic drama billions of years in the making. We are reminded of the interconnectedness of the cosmos, the delicate balance between life and death, and the awe-inspiring power of the universe we inhabit. Section 1. The Cosmic Circle of Life. Supernovae are the ultimate testament to the universe's grand cycle of life, death, and rebirth. They are cosmic engines of destruction and creation, shaping the universe we know and paving the way for life itself. In their fiery deaths, stars become creators, scattering the seeds of planets and possibilities across the vast expanse of space. Imagine those first generations of stars, massive and short-lived, lighting up the early universe with their brilliance. Their explosive deaths, like cosmic shotgun blasts, seeded the interstellar medium with the heavy elements necessary for the formation of rocky planets and, ultimately, life as we know it. Without those ancient supernovae, our own solar system, our planet, and even we ourselves would not exist. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the hearts of dying stars. We are, quite literally, children of the stars, our very existence intertwined with the life cycle of the cosmos. Section 2. Our supernova connection. The next time you gaze up at the night sky, let your eyes wander beyond the familiar patterns of the constellations. Seek out those faint, fuzzy patches of light, the nebulae, those cosmic nurseries where stars are born, and where the remnants of dead stars provide the raw materials for new generations. Remember that each and every one of those stars has a story to tell. A story of nuclear fusion, stellar evolution, and for some, a spectacular demise as a supernova. And remember that we are a part of that story, connected to the cosmos through the intricate web of cosmic history. The study of supernovae is more than just an academic pursuit. It is a journey of self-discovery, a quest to understand our place in the grand tapestry of the universe. It is a reminder of the beauty, power, and interconnectedness of all things, from the smallest atom to the largest galaxy. So keep looking up, keep questioning, and keep marveling at the wonders of the cosmos. The universe is full of stories waiting to be told, and each new discovery brings us one step closer to unraveling the mysteries of our cosmic origins.